Hello everyone, welcome to lecture 4 of week 10 of the course Power Network Analysis, in which we continue with the discussion on the fault analysis module. We will continue with the unbalanced fault analysis discussion that we had in the last lecture, in which we extensively talked about Fortescue's theorem application to understand the analysis behind evaluating fault currents for single line to ground fault and for double line fault. For single line to ground fault, we had chosen the specific case of phase A to ground fault. By the way, the single line to ground fault is also analogous to phase to ground fault. So, the notions of line and phase, they are interchangeable in the context of fault analysis. We had taken the case of phase A to ground fault, where we choose phase A as a reference for sequence components, and on similar lines, if one has to analyze phase B to ground fault or phase C to ground fault, then phase A can act as a reference for sequence components, but it is suggested that for phase B to ground fault, choose phase B as a reference for sequence components and phase C as reference for sequence components in C to ground fault. Reason being, with choice of phase A as a reference for sequence components, all the three faults can be analyzed, but in B to G and C to G fault, it will be difficult to draw an equivalent circuit of how the sequence networks would be connected for B to G and C to G fault if phase A were to be chosen as a reference, because the current relationship, specifically the sequence current relationships, becomes different. And that is what a simple suggestion goes by in terms of choice of reference for sequence components. Similarly, for double line fault, we had taken the case of B to C fault, fault between phase B to C, and we chose phase A as a reference for sequence component. Similarly, if you have to do C to A analysis, please choose phase B as a reference for sequence component, or for A to B fault, choose phase C as a reference for sequence component. The reason remains the same, that if we choose this as our reference for sequence component as per the respective faults, there we would be able to visually draw equivalent circuit of how the symmetric components would look like. So, given that, in today's discussion, we will start or understand the last category of asymmetric fault, which is double line to ground fault or double phase fault, and we will also understand the application of Thevenin's theorem in addition to Fortescue's theorem to understand or analyze the occurrence of faults elsewhere in the network. Could be on a transmission line, bus, transformer, and not just at the terminal of the three-phase synchronous generator, which we had considered in the last lecture also, as well as in today's lecture. This lecture we will consider the analysis for phase B to C fault at the terminal of the generator or very near to the generator. So, what we have here is a similar synchronous generator which is unloaded, and a phase B to C fault has B to C to G, that means double line ground fault, two phases or two lines and a ground also involved. These two phases are shorted to the ground through a fault impedance ZF, and since the generator is unloaded, the corresponding phase A current is 0. For simplicity, we are ignoring the impact or effect of mutual coupling between the phase impedances of the generator, although if one has to consider the impact of mutual coupling, it can be done on similar lines as it was done for three-phase balanced load sequence impedance. Even if the generator was to be loaded, the level of change of current in phase A with respect to phase B and phase C would be very, very marginal, and hence it is safer to have this sort of a assumption where phase A current is almost 0. After the fault has occurred, if we apply KVL between phase B and phase C to the ground, we get VB is equal to VC is equal to IF into ZF, and the fault current value is equal to sum of phase B and phase C currents. So, the way we applied Fortescue's theorem in double line and line to ground fault, similar lines we will also apply for double line to ground fault on these three indicative equations. So, we choose phase A as a reference for sequence components, and since phase B voltage and phase C voltage are equal. So in terms of the corresponding sequence voltages, that is VB in terms of VA0, VA1, VA2, because we have chosen phase A as a reference for sequence components, we can get a relationship in terms of sequence voltages based on the condition of KVL between phase B and phase C, which indicates that the positive sequence voltage would be same as the negative sequence voltage. And remember, for the positive sequence circuit, maybe I should reiterate a bit, the positive sequence network, it consists of an active source EA1, which is the internal EMF of the generator, in series with the positive sequence impedance, the current being positive sequence current IA1, and the terminal voltage of this positive sequence network is nothing but VA1. For zero sequence and negative sequence, the circuits are passive. That means they don't have any voltage source along with them. And for negative sequence current, we have IA2, Z2 as the negative sequence impedance, and the terminal voltage is VA2. Similarly, for zero sequence circuit, we have Z0, IA0 as the current, outgoing current, and terminal voltage being VA0. So this is for positive, this is for negative, and this is for zero sequence. For double line to ground fault, what we are getting is that the terminal voltage of negative sequence circuit should be same as the terminal voltage of positive sequence circuit, which is an indication that the positive and negative sequence circuits, for voltages to be equal, these two circuits have to be connected in parallel. That is one clue that we would get. Also, phase A current is almost zero. That means the sum of positive and negative sequence currents is equal to negative of the zero sequence current. So we have two facts, fact number 1 and fact number 2. If we combine these two facts, from fact 1 we get that the positive and negative sequence circuits have to be parallel because the voltages are equal to each other. And if this KCL equation has to be true for the second fact, that means that positive and negative sequence, they are parallel to each other and they are connected in anti-series in some fashion to the terminals of the zero sequence circuit. How that connection would look like, we still haven't reached there. That's where we would use our third equation, where the fault current is in terms of the zero sequence current, and I think there is a step which has been missed here, in the sense, yeah, that step is actually present over here. The corresponding circuit has been given earlier, pardon me for that. But this connection of 3ZF, how it is coming, we haven't arrived at that yet. What we got was that the positive and negative sequence voltages have to be in parallel because of fact number 1, which is this fact. And because of fact number 2, these two circuits, when they are in parallel, they have to be connected in anti-series to the zero sequence network. So that is what is giving us fact number 2. How 3ZF is coming in? It is coming in because of the discussion given in the next slide. By KVL, phase B voltage or phase C voltage is IFZF. So if we decompose our phase voltages into respective sequence components, this in a way would tell us that the positive sequence voltage is equal to, with some factor of A square plus A. Basically, if you recollect the property of A, where A was the complex operator at an angle 120 degrees, then as per this A definition, 1 plus A square is equal to 0, and 1 plus A plus A square being equal to 0, which would mean that A square plus A is equal to minus 1, and that is how VA1 is equal to VA2 is equal to negative of IA0 component. VA1, VA2 are equal. So with this sort of a combination, we are able to indicate that if VA1, VA2 have to be equal to each other, which is the voltage appearing across these two nodes, VA1 is equal to VA2, and this has to be equal to negative of the current, zero sequence current, with the corresponding zero sequence impedance and 3ZF. This would indicate that if IA0 is the current over here, then this voltage has to be equal to voltage drop across this impedance as well as this impedance, and that's how the 3ZF term is coming in. So I hope that explanation is satisfactory, and once we know the circuit arrangement of how the sequence networks would be connected, then in that case we can find the individual sequence currents IA2, IA0, IA1, and eventually we can get the function of IF, which is the fault current. So what we observe here is that in case of ground faults, be it double line to ground fault or line to ground fault, the zero sequence network comes in, because whenever there is a ground fault effect, the zero sequence current becomes live depending on how the zero sequence current flows or doesn't flow. Means Z0 being 0 or infinity is a separate matter, depends on how the transformer connections are. But if we have faults which don't involve ground, like three-phase fault or double line fault, the zero sequence network or circuit would never ever come in. In fact, for balanced faults, it is only the positive sequence network which matters. For double line faults, it is the positive and negative sequence network which matters, where they are in anti-series to each other. And in line to ground fault as well as double line to ground fault, all the three sequence networks come in. Basically, positive, negative and zero, they are connected in a particular fashion or a manner. The connections are, however, different. So now with this, if we have to extend this discussion for occurrence of any of these four faults, balanced or the three unsymmetric faults, on a point anywhere in the network, in the power network, then how would you do that? So that is where the Thevenin's theorem approach comes in. We have extensively talked about Thevenin's theorem application for balanced faults. Now for balanced faults, Fortescue's theorem need not be applied, because it involves only one positive sequence network circuit, the analogous circuit, which is usually there because of inherent generation of positive sequence voltage in synchronous generators. But for asymmetric faults, Fortescue's theorem is important, and that's where we need combination of Fortescue's theorem and Thevenin's theorem to understand unbalanced or asymmetric faults at any point in the network. Let that point be bus K with the fault having some impedance ZF. And since we are talking about faults occurring on transmission network, which are usually balanced, that means they are inherently operating in the positive sequence voltage or positive sequence current indication. So with the assumption that the pre-fault system is already balanced, to be specific, it is already operating in the positive sequence mode. That means the voltages are positive sequence voltage and currents are positive sequence currents. Then in that case, how do you go ahead with asymmetric fault occurrence? So what do you do? The way we tried to find Thevenin circuit in Thevenin's theorem application, that means you need the Thevenin voltage source, which is the pre-fault voltage source, and the Thevenin impedance, which was extracted from the bus impedance matrix, which was basically obtained from the bus admittance matrix. So we actually evaluate the positive sequence and negative sequence admittance matrices. The process of evaluating these admittance matrices is exactly the same as we discussed in load flow analysis, but the difference here is that in power flow analysis, we never ever considered the generator's reactance. To be specific, the steady state reactance was never ever considered. For fault analysis, while evaluating the admittance matrices, remember that all our synchronous machines, to be specific, these can be generators or motors, they are represented by their internal EMF, assuming that they are unloaded or loaded, in case the internal EMF will be different from terminal voltages, and the subtransient direct access reactance being present in series between the internal EMF and the terminal voltage. So point that I am trying to make is that for positive and negative sequence admittance matrices, one has to consider the presence of J XD double dash in addition to transmission line parameters and transformer parameters. For zero sequence admittance matrix, the evaluation process would remain the same as discussed above, but depending on transformer configuration, whether it is star connected, star grounded, delta, the one which we discussed last lecture, depending on that, the zero sequence admittance matrix has to be carefully obtained. Extensively depends on the transformer connection, as I mentioned. That means for delta transformer, the transformer in leakage reactance or impedance will never ever come into picture, because there is no path for the zero sequence current to escape out of the terminals. For star connected and delta connected configuration, in star connection, zero sequence current cannot flow, because the neutral is never ever grounded to the So on the HV or primary side, if zero sequence currents can't exist, here also zero sequence current won't exist. So except in star grounded transformer, we will have the transformer leakage reactance coming in while evaluating zero sequence admittance matrix. Similarly, for generators which are ungrounded, if the neutral is not grounded, then the corresponding zero sequence impedance of generator becomes infinite, and hence the corresponding admittance matrix will have a zero element in the corresponding evaluation. So these aspects, they have to be carefully kept in mind while evaluating these matrices. Once you know these matrices, you can invert them and the corresponding k comma k elements. Why k comma k? Because the fault location is bus k. So for finding the Thevenin impedance with respect to bus k and the fault point, it could be the neutral or the ground, Thevenin impedances would be k comma k elements of the respective zero sequence, positive sequence and negative sequence impedance matrices. And once these are known, we can for sake of convenience choose phase A as a reference for symmetric components, and for a line to ground fault to be specific phase A to ground fault. The way we evaluated the corresponding sequence currents in terms of fault impedances, this expression, it is exactly the same expressions as we saw in the last lecture. The only difference that you would observe here is, instead of ZKK0, we had just the Z0 impedance, which was the zero sequence impedance of the generator. For ZKK1, instead we had Z1, which was a positive sequence of generator, and ZKK2, instead of that we had Z2, which was the negative sequence impedance of generator. Now since the impedance position has changed, fault location has changed, so we are replacing these impedances by the respective Thevenin impedances. For phase B to ground fault, you may wonder or question what would be the fault current or sequence current evaluation. The component or expressions would remain more or less the same. In fact, they would be exactly the same, provided if you choose phase B as a reference for sequence component, and instead of phase A numbers coming in, here you would have IB1, IB0 and IB2. Even if you choose phase A as a reference for phase B to ground fault, the expressions will remain the same, only the physical realization of circuit won't be possible. For double line fault, specifically B to C fault with phase A as a reference, the expressions remain the same. There is no ground involved, there is no zero sequence involved. So zero sequence current is 0, and the positive and negative sequence current, they are in anti-series to each other, as we had seen in double line fault. For double line to ground fault, the expressions are again analogous to what we saw on slide number 6 here. If you compare these expressions with the expressions given over here as well as over here, then the numbers or formulas given in slide number 9, they exactly match the previous expressions, only that here we have the impedance matrix elements coming in instead of actual impedances. So the question then remains is, having known the Thevenin impedance, that what is the Thevenin source? The Thevenin voltage source is the pre-fault voltage source, which in case of no load is same as the terminal voltage of the bus itself. Since you may question or wonder, okay, we have been using E as the internal EMF voltage representation, how come it becomes same as the pre-fault voltage at the bus where the fault has occurred? Okay, the explanation is very simple. Bus K where the fault has occurred may or may not have a generator connected to it. So in case there is no generator connected to it, maybe it is just a load bus with no rotating load. So in that case, what is the internal EMF of that particular bus? Since there is no generator, there is no notion of internal EMF. That is point number 1. Point number 2, when we were discussing Thevenin's theorem application for analyzing balanced faults, did we ever consider the internal EMF of generator? No. We had taken up the fault location to be the bus K fault, where a three-phase solid fault or a ZF fault has occurred, and we chose bus K pre-fault voltage as the Thevenin pre-fault voltage. So if we combine points number 1 and 2, that in case there is a fault at bus K with no generator connected to it, then the internal EMF of generator would be same as the fictitious load bus or the pre-fault voltage bus, and Thevenin's theorem, it clearly explains that the pre-fault voltage is to be used to find the corresponding fault currents. So that is the reason why for pre-fault condition, even if the bus K has a generator or doesn't have a generator, we would use its pre-fault voltage condition to use the corresponding Thevenin application with Fortescue's combined together. So with this as our voltage, once we know the Thevenin voltage, we can find the corresponding sequence currents, and once we know the sequence currents, depending on the type of fault, we can use the Thevenin's theorem application to find all corresponding sequence post-fault voltages as per the corresponding buses. Capital Zik is the I, kth element of respective 0, positive and negative sequence impedance matrix. Once we know the post-fault voltages, we can use the A matrix, capital A matrix transformation to get back our individual phase voltages at all the buses in the power network. On similar lines, the way we can find the phase voltages, we can find the corresponding phase-wise current injections using the capital A matrix, because these currents we have already known based on the corresponding fault which has occurred. So essentially, in the pre-fault condition where the load is not present, all bus injections would be 0 except the post-fault condition at bus K. So once we know the corresponding phase current injections at different buses in the no load condition, we can use this A matrix also. How do I get the line currents? It's always suggested to use or do all the evaluations on sequence basis first, and then transform the sequence components to corresponding phase components, specifically in case where you have transformers of dissimilar configurations. So it is always suggested to carry out the evaluations in the sequence mode first, sequence components first, and then at the last end stage use the capital A matrix transformation to revert to phase quantities. The same notion is done for the corresponding sequence currents on the lines, where small zj were I0, ij1, zij2 are the actual sequence impedances of the lines, which is obviously known as per the transmission and parameter evaluation. And once the sequence currents are obtained, depending on whether the transformers configurations are similar or dissimilar, please revisit the transformer module and per unit analysis module, where we extensively talked about this phase shift configuration, that in case there is a transformer of dissimilar configuration, let's say one side is delta, the other side is star, whether the star is grounded or ungrounded, that is not important here, because as long as star-star configuration exists, phase shift won't happen between the primary and secondary quantities. Capital P here refers to the primary side of the transformer, and S here refers to the secondary side of the transformer. If we have evaluated our sequence currents, which are the currents shown over here, if we have evaluated these currents, then specifically with respect to positive and negative sequence current, in case of delta star or star delta transformer, if we have to convert, let's say let me choose the notation here, okay, Ij A1 post, which I have evaluated on the secondary of the transformer, which is star connected, and I want to find the same current on the delta side of transformer, then as per the star delta phase shift, this current should have a 30-degree lag on the secondary of the delta side of transformer. So basically, the secondary side here would be Ij A1 post with additional phase shift of minus 30 degrees. Similarly, if I have evaluated this current on the primary side, then if I move from delta to star, I will have a plus 30 phase shift. This is only for positive sequence current. For negative sequence current, the reverse phase shift would happen, because these phase shifts that we had discussed was assuming the fact that our network is operating in balanced condition where inherently positive sequence currents and voltages exist. As the sequence current changes, the orientation of the phase shifts would also change. So basically, if let's say I have found Ij A2 post on the primary of transformer, which is connected in star configuration, and I want to find the same current on the secondary delta side for negative sequence current, then this would be Ij A2 post with, instead of having a phase shift of minus 30, this would have a phase shift of plus 30. That is what is meant by reverse is true for negative sequence currents, because the notion or orientation of sequence itself has changed. These phase shifts as they have been drawn here, they are applicable for A, B, C sequence, which is the inherent positive sequence nature of generation of voltages or current. For negative sequence current, this sequence is A, C, B in clockwise direction. So if A, B, C leads to a phase shift of plus 30 from delta to star, the same ABC phase shift would bring in a phase shift of minus 30 from delta to star. That's where the reverse nature is. And so this is all about positive and negative sequence component. You may question, sir, what is there for the zero sequence current? What is to be done with IIJ A0 post? So the answer is very simple. If I have been able to find a non-zero value of IIJ0 post, which is the zero sequence current in the post-fault condition, then please revisit the last to last lecture discussion where we were talking about sequence impedances of transformers for dissimilar configurations. If I have a zero sequence current, which should not exist first of all, that's what I said, because here I have a star ungrounded condition. So most likely, in fact not most likely, obviously you would find a zero current on this side. This non-zero current may exist on the delta side of the transformer, but either ways, if you are able to find the zero sequence current on either side of a transformer which is having dissimilar configuration, because the configuration is dissimilar, the zero sequence current won't get transformed on the other side, because the terminals won't be able to experience those zero sequence current because of dissimilar configuration. As I mentioned, only in case of star grounded transformer, if I have found IIJ A0 post on one side of the transformer, the same current would flow over here in the same quantum with no phase shift required. Otherwise, in delta star or star star or delta delta connection, the currents on the primary of the zero sequence currents on primary of the transformer won't get passed on to the secondary at all, because currents can't escape because of dissimilar configurations. So after incorporation of relevant phase shifts in positive and negative sequence currents, now when you apply the capital A matrix operation, you will be able to get the actual phase currents, and that is where the sequence current relevance is important. If you have a power network where such dissimilar configurations of transformers don't exist, then essentially you need not evaluate or do this step. For transformers with dissimilar configurations, specifically star grounded and star grounded, if you try to evaluate the phase currents in the lines with respect to these phase voltages of the buses, you would get exactly the correct same values as we have done in the corresponding phase shift. But in case you wonder that, okay, I have a star star transformer, and can I still apply or find the corresponding phase line currents from the corresponding phase bus voltages? You have to be extremely careful in doing that, because in this sort of a configuration, zero sequence current will never ever pass from one side to the other side. So it is always safer to evaluate the sequence currents of buses, sequence components of voltages, sequence components of line currents. After you have done with all sequence components, incorporate the relevant phase shifts if they are required, and at the end try to make use of the capital A matrix to find the corresponding phase voltages, phase current injections and phase line currents. So that's all for this discussion. We will take up two numeric examples at length in the next lecture to further understand how do we actually do the asymmetric fault analysis using Thevenin's theorem and Fortescue's theorem for actual power network. Thank you.